Yeah, welcome everybody to the virtual winter school. My name is Benjamin Helmich-Paris, and I would like to tell you how to run CASSCF and multi-reference calculations using ORCA. So before we dive into the technical details, I would like to remind you when we actually need multi-reference methods. So we need multi-reference methods whenever we have a competition of many Slater determinants in the wave function expansion. And in that cases, we talk about strong correlation. So the simplest system where you can investigate strong correlation is the potential curve of the hydrogen molecule. So in a simple minimal basis set ansatz, we can position on each hydrogen atom a single S function. And from those two S functions, we can build a bonding and an anti-bonding molecular orbital. With these two molecular orbitals, we can build two Slater determinants that are singlet and also totally symmetric and can be used in an expansion to describe the ground state potential curve. In these two determinant ansatz, we see that at the equilibrium, the exact wave function is well represented by the Hartree-Fock determinant. However, when we start to elongate the hydrogen bond and have a situation where the two hydrogen atoms are far apart, the wave function becomes a mixture between the Hartree-Fock determinant and the doubly excited determinant. As you can see here in this figure, the Hartree-Fock determinant ansatz is way too high compared to the full CI result, where we have two determinants. It actually describes here an ionic dissociation into a proton and a hydrogen anion. If we use a correlated method based on perturbation theory, like MP2 on top of the restricted Hartree-Fock solution, we get here very unphysical results. So this textbook example can be carried over to more chemically interesting systems. For example, transition metal complexes that are open shell. They have a similar situation like a stretched H2 molecule. For them, you need multiple configuration state function to describe the near degenerate states. In this case here, for this cobalt complex, the near degenerate or the exact degenerate ground state correctly. Also, there are other cases like the ozone molecule where you have an open shell singlet, or as you have learned, if you want to describe bond elongation, dissociation, and transition states, you also need multi-reference methods. If you want to describe doubly excited states in large chromophores, it's also necessary to use multi-reference methods for this. So each multi-reference method makes a configuration interaction wave function ansatz. So we do a linear expansion of our wave function in terms of many Slater determinants or configuration state functions, which are spin adapted or spin and even symmetry adapted Slater determinants. So the simplest multi-reference method is the multi-configurational self-consistent field method, for which we minimize the energy with respect to rotations in the orbital and CI coefficients. In addition to this linear CI ansatz, we also have here this orbital rotation operator that helps us finding the optimal orbitals. One of the advantages of multi-reference methods is that we have a very simple access to excited states. So with the state averaging approximation, we can treat excited states and ground states at the same time whenever we have the same orbitals. We can obtain the solution very easily by finding the lowest eigenvalues and eigenvectors of the large CI matrix. The state average CASSCF method is then defined by finding optimal orbitals and optimal CI coefficients by minimizing an averaged CI energy. The weights for each of the states is usually fixed. So in principle, our multi-reference calculations could be very accurate. However, the problem is that the number of Slater determinants or configuration state functions that we can construct grows exponentially with the number of orbitals and number of electrons. If you have only 2 electrons in orbitals, you can construct 4 Slater determinants. If you then create from those 4 Slater determinants configuration state function, you have 3 singlet functions and 1 triplet function. However, 2 electrons and 2 orbitals is not really highly practically relevant. Most molecules have much more orbitals and much more electrons. If you go to 18 electrons and orbitals, you already have over 2 billion determinants. The number of configuration state functions is also very high and also grows exponentially with the number of electrons and orbitals. So even today, full CI calculations have no actual relevance in practical applications. So practical multi-reference methods do a full CI expansion by distributing a small number of active electrons among a small number of active orbitals. So this usually then defines the so-called complete active space. By doing this, we separate the molecular orbital space in three parts, as shown here on the right. We have our core orbitals, which are always doubly occupied. We have the virtual orbitals, which are always empty. And then we have the active orbitals, which have a varying non-integer occupation number that depends on the CI expansion. There are different multi-reference methods you can construct following this idea of an active space. Having the CASSCF solution, we can also add here a second order energy correction to the CASSCF energy. This we do by perturbation theory. In perturbation theory, we split our Hamiltonian into a zeros order part, which describes the effective electron interaction, and then a so-called fluctuation potential, which describes the explicit electron dependency. Then we can collect all the terms in the Schrödinger equation that are first order. This can be casted in an operator form, and it can be shown that only two electron excitations with respect to the CASSCF solution are needed to calculate the first order wave function. With our first order wave function, we can then calculate our second order energy. There are also different types of multi-reference perturbation theory methods, which are defined by their zeros order Hamiltonian. The most prominent methods are the CASSPD2 and the NEFPD2, which are both available in ORCA. There are also more accurate methods like multi-reference CI and multi-reference coupled cluster. While in multi-reference CI, we still do here a linear expansion, including here this excitation operator. In multi-reference coupled cluster, we have here an exponential parameterization where T is included. There are also methods that combine CASSCF with DFT to have here a low-cost multi-reference method. Those will be available in the next ORCA release. The multi-reference methods that I've just introduced can be quite accurate, but also quite expensive. They have a high polynomial scaling with the system size as their single reference analogs. However, the computational prefactor is much larger, in particular for multi-reference coupled cluster, multi-reference CI methods. So now I would like to focus here on one particular example to explain you how to run multi-reference calculations using ORCA. And this is the twisting of ethylene. Twisting of ethylene is an important pathway in photochemistry, because if you twist here the two planes defined by the carbon and the two hydrogen atoms, you reach a maximum in the ground state, but the minimum in the excited states, in the valence excited state where you have promoted one electron, and also in the doubly excited so-called zwitterionic state. The twisted conformation at 90 degrees is an open shell singlet state like the stretched H2. It should therefore be treated with multi-reference methods. A single Slater determined ansatz would result here in a faulty ionic state at the twisted conformation. If we would like to run your multi-reference calculation with ORCA, we have to answer a few very simple questions. So which orbitals should be placed in the active space? Well, this is fairly easy because only these frontier orbitals change as we twist the ethylene structure. This means that we only put in here the pi and pi star orbitals, which are closest to the HOMO-LUMO gap in the active space. 2 electrons in 2 orbitals. So the second question that must be answered is what is the number of states, or what is their spin, and also what is their spatial symmetry if we want to exploit that. So at the moment we are just interested at the ground state. So this is then one state with singlet symmetry. There are plenty of options how to generate starting orbitals. For very simple molecules like ethylene, it's sufficient to start from DFT orbitals or just use the normal model Hamiltonian gas that you would also use for Hartree-Fock or DFT calculation. So here you see the results of a CASSCF calculation. On the left, we have the planar calculation where the CASSCF energy is printed, and also the leading configurations in the wave function expansion. You see that the leading configuration is the Hartree-Fock determinant where the pi orbital is doubly occupied. For the twisted conformation, the energy is higher, and the wave function is a 50-50 mixture between these two configurations, where one of the orbitals is doubly occupied and the other one is empty. So now let's move on and calculate now the potential energy surface. We can do this in ORCA very easily by the scan feature, where we specify internal coordinates and then have a list of dihedral angles, for example. To calculate not only CASSCF, but also NFPD2 and MRCI, you can just use here this simple input keywords, and you easily get your NFPD2 and MRCI energy calculation done. On the right, you see the potential energy curves using restricted Hartree-Fock, CASSCF in green, NFPD2 in blue, and multi-reference CI. The multi-reference results here are very close to each other. Only the restricted Hartree-Fock result is way too high and has here this unphysical cusp at 90 degrees. If we now make here a small inset for the dihedral angles between 80 and 100 degrees, we see that NFP2 is actually slightly higher in energy than CASSCF, and multi-reference CI is slightly lower in energy than CASSCF. As I've said, we can also easily calculate excited states with CASSCF. We just have to increase the number of roots in the CASSCF input block. Again, we do the same type of calculation. We do a scan of the ethylene where we twist the two CH planes from 0 to 180 degrees. And at each point, we calculate the CASSCF, the NFPD2, and the multi-reference CI energy of the three states. For the ground state, we still have a barrier at 90 degrees. And for the singly excited state and the doubly excited state, we have a minimum at 90 degrees. Again, NFPD2 and MRCI, the more accurate methods, give very similar results, and the excitation energy is significantly lower than with CASSCF. So here I would like to summarize the small introduction to how to run multi-reference methods with ORCA. So only use multi-reference methods whenever you have near-degenerate states. If you don't have that, don't use them. There are much simpler methods available. However, multi-reference methods should be used whenever you study potential energy surfaces and if you have open shell molecules. The complete active space self-consistent field methods is one of the simplest multi-reference methods. It is doing a full CI expansion with a small number of active electrons and active orbitals. The number of active electrons and the number of active orbitals you have to specify in the input. You also have to specify the number of states you would like to include and what's their multiplicity and maybe even what's their spatial symmetry. We can easily describe excited states by using the state averaging approximation. For state averaging, you use the same set of orbitals but have different CI solutions that are specific to every state. CASSCF, however, is not the most accurate method. It lacks a sufficient description of dynamic electron correlation. In ORCA, we also have more accurate methods available. The most prominent ones are based on second-order perturbation theory and are called NFPD2 and CASSPD2. If you need higher accuracy, you should also use multi-reference configuration interaction or even multi-reference coupled cluster methods, which are also available. If you want to learn more on multi-reference methods and how to use them with ORCA, please have a look at the ORCA manual, which is available online. There are also plenty of reviews around, for example, the one of Lischka on multi-reference methods for excited states, and also the one of Nese for multi-reference methods in the field of transition metal complexes. If you have further questions, please don't hesitate to contact us via email or visit the ORCA forum and leave a post there. Thanks a lot for your attention.